Welcome to the 7.2 video for Math 31, which is where we start to examine no more of those limits. We're going to actually look at the derivatives of our sine and cosine function, and that's going to extend in 7.3 to 10, and certainly the reciprocal trig ratios as well. But before we do that, I think it's useful to talk about, and really this is one of those things that you could just look at a formula sheet and you could memorize. But we want to avoid doing that as much as possible because you only have realistically so much functional memory to memorize things like this. So if we understand where the derivative comes from, then we're not memorizing, we're understanding, and it's very, very, I think, well, it's more difficult, I think, to lose understanding than it is to lose memorization. So if we were going to graph, and I'll put in blue here, y equals sine x, then what we would have is, and I've made this scale just kind of a reasonable scale for y equals sine x, and I'm going to plot the points that we know. Well, we know that the sine of 0 is 0, 2 pi is coterminal with 0, and so is negative 2 pi. And that makes it easy to have a kind of a starting point. The sine of pi is also 0, and therefore the sine of negative pi is 0. Now, this is from your unit circle knowledge. The sine of pi over 2 is positive 1. That also means that the sine of negative 3 pi over 2 is positive 1, just using those coterminal angles. The sine of 3 pi over 2 is negative 1, which means that the sine of negative pi over 2 is negative 1 as well. Now, it's not perfectly symmetrical, but it's close enough that if we were to join these points with our knowledge of trig, then what we get, again, other than my bad drawing skills, is a graph that looks something like this. So that's y equals sine x. Now, what we want to look at below is how can I use the graph of sine x to see what the graph of the derivative would look like? And the easiest way by far is to take a look at the slopes of that graph in blue. And I'm going to do that with red lines here, and we're going to identify the easiest points, and hopefully after chapter 4 and chapter 5, you have a pretty good handle that anywhere we have a min or a max, we have a slope of 0. So right here, 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 and here, this graph has a slope of 0. Now what that means is the value of the derivative is 0. So the derivative of sine x has a value of 0 at pi over 2, a value of 0 at 3 pi over 2, and a value of 0 at negative pi over 2, and finally at negative 3 pi over 2 as well. All right, now those are the easier ones. The next thing we're going to do is we're going to try to find the regions where it has a slope of 1. That occurs at these points. And I'll just write beside it that this is where my slope is equal to 1. And one more all the way over here at 2 pi. And that allows us to plot points again. So the slope of sine x is 1 when x is 0. It's 1 when x is 2 pi. And finally, it's 1 when it's negative 2 pi as well. All right, last kind of easy point to talk about is when the slope is negative 1. Some students struggle with the idea of, how do you know the slope is negative or positive? Try to remember that when we talk about slope, we are talking about the rate of change of the graph as we go left to right. So if the graph is decreasing or moving down, it's negative slope. If it's increasing or moving up, it's positive slope. Well, knowing where my slope is negative 1, again, we can fill that in. It's negative 1 at this point. It's negative 1 at this point. And if I connect those dots, what I get is this graph. Now, this may not look familiar to you depending on how much you remember trigonometry, but that graph in red is actually y equals cos x. Now, what this allows me to say is because we use the slope concept and the derivative concept on my sine x graph, then what I can say is that the derivative with respect to x of sine x, or the derivative of sine, is cosine. And this is one of those things that a lot of students don't like trigonometric derivatives because they never really get simpler. And I shouldn't say never, they rarely get simpler. And the logic behind that is if you took the derivative of sine, you get cos. Guess what you get when you take the derivative of cos? And we're going to do that in a visual investigation next. But therein lies the issue with, sine or cos, that if we did, because they're periodic functions, try to figure out how many inflection points they actually have infinite inflection points. They have infinite mins and maxes, just like they have infinite x-intercepts. So very, very important, just like in 30-1 math, when we are examining the graphs of y equals sine x or y equals cos x, we have to be pretty aware of any restrictions on the variable. All right, we're going to do this with cos, so I'm going to keep it the same color code I had before. I'm going to make y equals cos x my graph in red. I'm not going to belabor this one as much as I did the other because I know that we just did it, but the graph of cos x, a little exaggerated dip there, but that's okay, looks something like this. There we go, that's not bad. And then we can do the same thing we did before. I'm going to do it in, I guess, maybe green this time. I'm going to identify the slopes of my y equals cos x graph. Well, we have a slope of 0, at pi, and at negative pi. Technically, it is also 0 at negative 2 pi and positive 2 pi. My graph doesn't really do that justice, but we'll talk about, the connection between those points as we go. So I'm going to do these in green. I'll probably not draw the graph in green, but what we see happening is we have these values where my derivative is equal to 0. Now, right away, the fact that the derivative is 0 on the origin is a pretty big shout out that this might be related to sine x. There's a problem though, and that's, we run into it as we do the positive slopes. So we have a slope of 1 here, a slope of 1 there, and that's it. So this is going to be positive 1 at 3 pi over 2, and it's going to be positive 1 at negative pi over 2. Oh, what did I do there? No, that's right, sorry. We do have to fill in the negative values then. It is negative at pi over 2 and at negative 3 pi over 2. So we get a negative 1 here and we get a negative 1 here. Now if I connect those dots, I get this. Now my question to you, is that the graph of y equals sine x? And, fortunately in your notes, these are kind of right below each other on the same page. So you should be able to track up and say, no, that's not y equals sine x. And we have to use a bit of our 30-1 knowledge and recognize that what this graph is, I'm just going to put sine x on here for a second. This is the graph of sine x. And it looks pretty confusing when they're side by side like that. But what happened is if we took this blue graph and reflected it, I actually don't know if this is going to work. It might not. No, it doesn't. But if we reflected that across the x-axis, what we get is our green graph. So this graph that I drew in green is y equals negative sine x. And so just like I made that statement on the previous page, we use the derivative to draw that graph. So the derivative of cos x is equal to negative sine x. And that is one of the trickier things to remember. Certainly the derivative of sine and cos are related to the other trig function, but the derivative of sine is just cos. The derivative of cos is negative sine. And that's a really, really crucial distinction to make. And we have to make sure we're really, really diligent with that. Now you have these in your formula sheet presented this way. I have to admit that this always drives me nuts because this is certainly the derivatives as we would normally do them. The problem is that they're showing these derivatives with nothing more complex than just a variable inside the trig. And that is not always going to happen. So the one thing that I am going to add on beside these is what if I'm taking the derivative with respect to x of the sine of a function? Well, what this becomes then is we take the derivative of the outer function, which is sine, so the derivative of sine is cosine. The function's still inside, so we would also have to multiply by the derivative of the inner function. Now, the logic for textbooks, I believe, is that because we've already taught you the chain rule, this is just applying chain rule to a complex function. But I really do think at least once it's nice to see that when we talk about taking the derivative of sine or cosine with an inner function, we take the derivative of the outer function, which is sine or cosine, and then we multiply by the derivative of the inside, which is pretty classic, chain rule. And I'm just going to write this a little bit of a different way underneath because I think seeing different notation is helpful. If you took d over dx of the cos of, let's say, u, this is equal to negative sine u times the derivative with respect to x of whatever that expression u would be. Now, what I wrote for cosine and sine are actually the same thing. You could replace u with f of x or f of x with u, but I think it's nice to see different notations because at the end of the day, not all of you are going to use the same textbook next year if you take Calc in university. So learning how to read multiple notations, I think, is a pretty big advantage. All right, let's do some of these. And definitely it's going to start off, easy is probably not the right word. It rarely is for calculus, but it starts off pretty straightforward, I think. So it wants us to differentiate the following. So I'm going to take d over dx of y and make it equal to d over dx of the sine of 4x. And that's just, again, being consistent with our notation. When I do that, the derivative with respect to x of y is 1, but we have to include our little Leibniz piece, which is dy over dx. The derivative with respect to x of the sine of 4x is the cos of 4x. But because there is an inner function, I have to multiply by the derivative of that. What's the derivative of 4x? Well, it's just 4. So we get that the derivative with respect to x of our y function, sine 4x, is 4 times the cos of 4x. All right, the second part of this lesson is just going to be looking at some of the, well, let's do one more example. There's lots here. So this next one, and this often does confuse students, they want to multiply by x minus 4. Remember though, when I do write, and I'll write it as y prime, we are going to have the cos of x minus 4, and I'm going to write it really explicitly here. We would then multiply that by the derivative with respect to x of the inner function. And that is just chain rule. Maybe take a look back at chapter 3 if you haven't done chain rule in a while. I know you have. It's been in plenty of the assignments. Y prime then is going to be equal to, I'm going to write this as the cos of x minus 4 multiplied by the derivative with respect to x of x is 1. The derivative of 4, or negative 4, with respect to x is 0. So I'm just going to keep that as 1. And so I get for this question that y prime is the cos of x minus 4. Now, if you're interested as why didn't this one have some other piece multiplied onto it, it really is because this function that we just finished, it's just y equals cos shifted 4 units to the right. That doesn't change how the rates of change happen, it just changes their locations. Whereas, and I'm just going to flip it back, the previous function was y equals sine x horizontally stretched by 1/4. That will change the slopes and therefore needs to affect the derivative as well. That's why those two questions are kind of fundamentally different. Okay, that's part 1. In part 2, we're going to do the rest of the examples and you'll have some chance to chip away at this.